Good morning, everybody. Um, Welcome to day 4 of the Spark workshop. For the first talk, we have Srijan Das. He is a graduate student from Princeton University and an alumnus of SESI. And he's going to talk on imaging magnetic fields in the sun and other stars. Srijan, you can proceed.
All right. Thank you, Yoshita. Hopefully I'm audible and visible. If at any point I'm not audible or something, just let me know. And with that, I'll start sharing my screen. Do you see my slides? It should be full screen by now.
Yes, we can see your slides.
Excellent. Okay. Hello. I'm Srijan, and I'll be talking about two of the projects that I have been working on as a part of my PhD at Princeton. And they mostly deal with magnetic fields and how you can image internal magnetic fields in the sun. So this is the talk, which is the recipe for imaging magnetic fields in the sun and other stars, which is to mean that I have not yet actually done an inversion, but I think we have the formalism to do it. Um, and I think this is a very nice opportunity to present it in front of people who are directly related with space weather, so that we can start thinking about how to connect the solar atmosphere to what's going on inside, which, as all of us know, is extremely important. So this image that I have in the very first slide is just a demonstration of what people have been able to achieve um, in terms of simulating a sunspot and how close it mimics what you can observe. So if I do not tell you which of this is, so on the two sides of the blue line is an observation and a simulation, to an untrained eye, it's pretty hard to distinguish. But on the left is what you have what you have from simulations, and on the right is what you have from observations. The fact that you can reproduce the observations this well through simulations is excellent, but then we never have been able to achieve how the magnetic structure looks like inside the sun through formal inversions. So the main reason is the absence of what I'll introduce you as sensitivity kernels. So let me go into the outline of the presentation. I'll first start with introducing the main features, which is called normal modes of the sun, that we use to extract all the information that's inside. Then I'll talk you through the idea of sensitivity kernels through a very dumbed down picture of a coffee cup. And I've used this before, maybe some of you have even seen it. And then we start with the things that I believe is new to the community and the things where we have contributed. This cryptic looking expression is the kernel. Unfortunately, this doesn't look neat, but so be it. And then we'll talk about how the same theory can be applied to a small patch on the sun, which is where the Cartesian mode coupling comes in. And finally, something we discovered from terrestrial seismology, which can be very immediately applied to the astrophysical cases as close as like 2 weeks back. I'll talk about this new basis called Slipian basis. So with that, I'll start. If at any point in the talk you feel lost, look at the panel above. On the left in the black patch is the broad topic, and on the right you have the subtopics I'm talking about. All right. Most of us, or all of us rather, know about Fourier Transform, but I'll still talk through this image. And I find this is a beautiful demonstration of how a signal, which is in blue, composed of multiple sinusoids, can be broken down into the components. And then when you project it back into the frequency space, you see just two peaks. So the entire time series can be actually represented by a very much reduced version in the Fourier space. But this is in 1D. As all of us know, the sun is a sphere, and what we observe is in a 2D spherical surface. So what we really need is not sines and cosines, but rather a basis in 2D. And okay, so this is how the basis looks like for 1D, but similarly in 2D you have spherical harmonics. The very first one is a constant all over the sphere, and this represents an analog of a flat string, which can just move up or down. And this first mode is called the breathing mode, where the entire mode moves out like that and moves in contracts. So this is how the oscillation manifests itself. Similarly, all the other spherical harmonics can have its own oscillation patterns and oscillation frequencies. And this is a demonstration of how different spherical harmonics can be summed up to produce any arbitrary structure, which is by the way, the concept of basis. To demonstrate this even more intuitively, there's a very beautiful demonstration of how the entire cosmic microwave background, which, as you know, is seemingly a random patch in the celestial sphere, can be decomposed into spherical harmonics. So what's shown on the top left is the power contained in each angular degree. And by angular degree, I mean the detail of the structure on the surface of a sphere. And as we'll see in the animation, as we go to higher and higher angular degrees, with its corresponding powers, we'll soon start emulating the entire cosmic microwave background. So we are starting off with very low angular degrees and keeping adding them one after another. And as you see by now, it's basically a random patch on the sphere. So anything that we have on the surface of the sun can also be broken down into spherical harmonics. So this is the sun instead of the cosmic microwave background, and these tiny blobs on the right, you see, have started to move with their own eigenfrequencies and their own eigenfunctions. As soon as you take all these and put some weights in front of them, 1, 2, 3.5, and add them up, you start getting whatever you see on the solar disk. And this is a very concise representation of if you take the entire sun, decompose it into the spherical harmonics, and then plot them as a function of the angular degree and the frequency at which that oscillates, and the color over here representing the power contained in each such channel. This is what you'll see. Each of the branches over here denote what we call radial order. I'm not going to go into the technical details of that. You can ask me later if there is a question. But let's just call that these are different labels that you associate to spherical harmonics, just like you would do for a hydrogen atom problem. So to summarize the process, you have a Dopplergram, which is the solar disk. Each pixel on the Dopplergram moves either towards you or away from you. If it moves towards you, it's a blue shift. If it moves away from you, it's a red shift. And you can take this entire Dopplergram, decompose it into all these different family of spherical harmonics, each of which will have its own frequencies. So this shows a time series of oscillations of a particular spherical harmonic, which is L equals 100, M equals 90. And then, again, the concise image is shown on the right. Okay, so after having introduced how the basis functions look like, let's move on to the very important concept of mode coupling. If you think about two modes as, one being an incident wave and one being a scattered wave, these modes are coupled by perturbations that exist in the sun. Now, whenever I'm talking about a perturbative analysis, there has to be something over and above which it's getting perturbed. So I will introduce the concept of a background in a bit, but if you have two modes, they represent a certain spherical harmonic, right? Because anything can be decomposed into spherical harmonics on a sphere, and so can the perturbations. And we'll see that the way these modes actually encode this perturbation is through an integral that involves the product of three spherical harmonics. You can think about this as some sort of a selection rules that starts happening. So in the first case, as you see, it's as an axisymmetric mode, and the perturbation is just a constant, so it's also axisymmetric. And the second mode that gets coupled to the first mode through the perturbation is also axisymmetric. And if you carry out this integral over the whole sphere, the spherical surface or the solid angle, you'll see that this is going to amount to a non-zero finite value. But then the selection rule starts playing in depending on the combination of the structures that's present in the modes as compared to the perturbation. So in the second plot, in the second row, once again, these are all axisymmetric, but this time you see that one of these is actually equatorially antisymmetric. So if you combine them, make a product, integrate it over theta and phi, it will amount to 0. And finally, if one of them is not axisymmetric, but two of them are, that's also going to go to 0. So this is a mathematical exercise, but physically what this means is that you can pick and choose your modes such that you can isolate these perturbations in terms of the channel or the labels of spherical harmonics they exist in. And this reduces your inversion and lets you, really fine tune it according to what exactly you want to infer. A popular example is differential rotation, and I'll come to that in a bit. So this was a pictorial image, but this is formalized through these mathematical entities called Wigner 3Js. None of this is important to remember, but just wanted to put it out there. Okay, so for people who do not use sensitivity kernels on a daily basis, this is a set of slides which hopefully will be useful. So think about your coffee cup or tea cup or whatever you drink, and think about a background state where you just go to the coffee machine, you put something in, you take the coffee, and it's all constant density. But now you add a layer of a sugar to it, and you add cream. So the sugar is going to go down and accumulate at the bottom. The cream will stay somewhere above. And the task is, given the background, given the knowledge of the density of the coffee, you need to find from what you see on the surface where that sugar layer is, where that cream is, and what is the associated density. So this is written through a very simple expression of f equals k times b, where, as we'll see later, b is whatever perturbation we are trying to invert for. In our case, in this example, it's the density. K is the kernel, or the sensitivity kernel, and that is, by the way, the main upshot of the study that I'm presenting. And f is the frequency that you observe on the surface. So in this plot, if the perturbation around the background is 0, which is when you have not added either sugar or coffee or cream, it's all 0, as you see here. And let's say the sensitivity that this physical system has to the density perturbation is constant throughout. So what we'll see is that in the absence of any perturbation, where you have not added a sugar or a cream, you would end up with no change in frequency. So whatever frequency you'll observe will be the characteristic frequency of the background medium. So that's why f of r is 0. So whatever you observe on the surface is what you expect. Next, let's say you have the sugar, right? And so there's a tiny bump in B of R, which represents the perturbation as a function of depth. That gets multiplied with unity, and it shows up in the frequency channel as a similar bump. Similarly, when you have the layer of cream, it gets multiplied with the kernel, which again, till now, is constant as a function of depth, and it has an equal response in what you observe. So up till now, what this is saying is, if you have a cream and sugar, and you put a drop on the surface after that, it'll ripple, and there will be certain eigen frequencies and eigen functions of those ripples. Possibly, you can decompose that in Bessel functions. And each of these ripples will have its own eigenfrequencies, which in the background state would be purely representative of what you expect. But as soon as you start having perturbations, the frequencies at which these ripples happen will start differing. And from observations, you can take a difference between what you expect and what you observe. And this difference encodes the information of the red line over here. Now, almost always what happens is the kernel is much, much stronger near the surface, and it dwindles as you go deeper and deeper. So what this means is, even if the density perturbation in the system is the same at a shallower depth and a deeper depth, the response of that in frequency is much, much stronger at a shallower depth. So anything near the surface is much, much well observed and constrained as compared to anything far deeper. And this is, to me, this is nature's way of telling that, look, you cannot look beyond this. There has to be some way of intuitively thinking that if the sun is an opaque surface and you cannot see something I mean, as you go deeper and deeper, of course, the sensitivity has to reduce. So kernels essentially emulate that, at least for P modes. So
Srijan, is there any way out whatsoever of this issue, of this problem, or you are basically stuck fundamentally with this construct?
uh, it depends
I mean,
on,
I know people do a lot of, when they do long-term observations, they try to use signal processing in terms of sort of integrating over time to enhance the signal to noise. But those are all post-processing kind of issues. But you're saying essentially theoretically this is a fundamental problem that you can never in principle. I mean, it's kind of a disheartening a little bit. But I
it's,
guess
cer-
Rahul
it's
will also comment on that. But yeah.
it certainly is, and this was one of the first things which I think as kind of matured scientist, I started looking at it in that sense that it's disappointing. Nature has noise, and there is no way around it. If in an ideal system there was no noise, you could see everything, which is what we do for synthetic tests. But as soon as you start having noise, that has a trade-off between uh, the small sensitivities that you have at shallower, at deeper depths. So this is exactly the reason, to answer your question, why G modes are defined to be the holy grail, because G modes have kernels which are sensitive at very close to the
Lower
core,
down.
right?
Mhm.
So as soon as we can identify a patch in the frequency domain where the G modes start talking to the P modes, uh,
Mm.
and exchanging information across the depths, that's when we can start
You
looking
can
deeper.
utilize that to get information out.
Yes,
Okay.
exactly.
Mhm.
All right. So now that we know what sensitivity kernels are, let's move on to the crux of the issue. So observations, which was F in the previous, so F here is observation, K is kernel, and B is the perturbation. And the integration over R just represents the fact that you are summing it up, collapsing it in depth with weights, which are kernels, and what you're observing is only at the surface. A fantastic example of this is differential rotation. And it has been possible to measure differential rotation this precisely because the kernels were there, and they were, yeah, they existed for a long time, and people have been using this to find very, very precise measurements of differential rotation. But in the absence of kernels, this couldn't have been done, which was fundamentally the case for magnetic fields. So if you write the same thing, but for magnetic fields, this red question mark over script B shows that this information or the analytical form of these kernels didn't exist until 2020 when we wrote our paper. So that is not to say that we are the first people to do this. Of course not. People have tried this before, and there has been very notable contributions from Gough Thompson in 1990, where they take axisymmetric fields, but of very precise geometrical structures like dipole or octoroidal, and they do a forward calculation. So by forward calculation, I mean, let's say you have a simple forward model, which is y equals mx plus c, which is a straight line. And you want to infer the slope, which is m, and the intercept, which is c. So you can just plug in the values, different values of m and c, and you try to uh, investigate how well that matches with the straight line that you have. But then this is a highly non-unique process when you have a very large number of m's and c's, which is a higher dimensional parameter space. So you can come up with n number of configurations in which this will be satisfied, which is what I mean by non-uniqueness, which is why forward calculations are not really the most optimal way to go about trying to image the solar interior. Um, so yeah, Gough Thompson, Zimbowski, they had done this for global modes, which means modes that are sensitive to the global structure of the sun. But you can also do similar things for a local structure, which we'll also come to later. And the main effort that went into this was trying to investigate how acoustic modes, when they hit, a very strong magnetized structure like magnetic fields or active regions, how that undergoes conversion to magnetic waves, which involves Alban waves, fast and slow magnetosonic waves. And as you can imagine, when a wave converts from an acoustic to some kind of a magnetic wave, the energy content in the acoustic waves would reduce, and that's precisely what people observe. So what is needed is a complete theory which takes into account uh, all these mode conversions. And that's where we come in. And our work is completely standing on the profound foundations of ideal MHD. And I would like to very much recommend this book by Hoodblood and Pertz, and as I'll show later, Friedberg's Ideal MHD, where you have a treatment where you start from the equations of ideal MHD. By ideal MHD, I mean it's non-dissipative. You don't have an eta term in the induction equation. And then you can linearize it. And this is the usual stability analysis that one needs to go through for any system when they're trying to decompose it into its characteristic eigen frequencies. When you do that, you end up with a linearized wave operator where it's just like, you just take the system, you perturb it in whatever way you want, and there will be tiny waves that will be going around. And depending on if the operator is Hermitian or not, these waves would either be stable or it would end up being unstable. Um, okay. And after a lot of algebraic manipulations, we end up with this form where you have a volume integral and you have a surface integral. I don't want you to think about all the mathematics right now, but just imagine this being two modes and then everything in between being the structure that these modes are coupling. The structure contains the pressure gradient, then magnetic fields and all sorts of things that you can imagine. Flows for differential rotation. Um, so what we really need to do is we need to look at this volume term because that's what contains and feels everything that's contained in the sun. And a very essential property that our super matrix, as we call it in helioseismology, which is just eta dot f psi, it should have is Hermitianness because or hermiticity, so that you can start getting stable results since we don't have dissipation in our system. So writing the same thing in a more understandable way, and this is just to convince you that look, this is all complete as far as I understand, is the first term is the shear Alban wave, which is just the Alban wave. And this is the potential energy, by the way. So if you find the potential energy of the entire system, some bit of it will be because of the Alban wave, some bit of it will be because of the slow and fast magnetosonic waves, which is the second term, compressional Alban wave. Third term would be just from sound speed or acoustic modes. Then you would start having these things called pressure-driven modes and current-driven modes. And these could be potential sources of instabilities. But in our case, what happens is when we write it out in the volume term and the surface is such that it extracts out all the non-Hermitian part. And thankfully, the eigenvalue problem is set up such that these modes actually dwindle down to zero, which is where our coupling becomes perfectly Hermitian. But all of these are details, but I just wanted to emphasize that we think we have a complete theory here. Okay, the main reason why previous studies which have tried to infer B as the perturbation have not really succeeded is because B is not really the invertible that we should be looking for. And that simply comes out when you try to look at the Lorentz stress or the Lorentz force, which is J cross B. Since you already saw that the inverse problem needs to be formulated as an observation times a perturbation, observation being perturbation times kernel, so you can imagine that all these perturbations need to be clubbed together. If you write J cross B as kernel of B cross B, it's like it's scattered in B, right? You need to club together these B terms. And since there are two B's, as soon as you start clubbing them together, it is the Lorentz stress that becomes the invertible parameter, which is demonstrated by the fact that the first term here is just the magnetic tension, and the second term is the magnetic pressure. And H from now on is just BB, the second rank tensor. So now you see I've color coded this in the exact form of observation is nothing but perturbation times kernel. And this horrendous looking B star here is the kernel. We did have to go through the painful task of doing some integration by parts to isolate the B as you see it here. But I believe it's much cleaner than if you look at the other papers I've referred to. So what did we do differently? We did only one thing, which was different, which is we tried to treat our perturbation in the correct basis. I've already showed you how any distribution on the surface of a sphere can be decomposed in spherical harmonics. But if that distribution is a vector, for example, velocity fields, you need vector spherical harmonics. But now, in our case, it's not a vector or a scalar, it's a tensor because it's b times b. So we start with generalized spherical harmonics. This has its own literature and its own identities, and it's extremely elegant. And you can use all these identities to end up with such a linear inverse problem. What I write as h over here is what the Lorentz stress, which is b times b, looks like in its generalized spherical harmonic basis. But then this cryptic h can be readily converted from to the bb that we know through these transformations, none of which you need to really remember. All of which all that I want to show here is that given a certain component of h, you have spherical harmonics, and you can get back b in the physical space.
Srijan, so as far as I can see, you're not really throwing away any terms. Is there any linearization involved anywhere, or you're keeping everything?
Oh, the linearization happened.
Did happen.
In getting here. In
kind
getting
of make sure. What did you do there? So what term did you throw out? I'm just kind of curious about that.
Oh, we just so we throw away terms which we call to be second order in perturbation. So here you see there are these subscripts ones, right? B1, P1. These are actually perturbations, and whenever you start having
So
terms,
physically, what would they correspond to? I'm just trying to figure out if those will be important in the convection zone or not.
So if you think about this,
estimates, or you try to justify that doing linearization is fair enough.
So doing a linearization is fair enough because from the background solar model that we have using all these different stellar evolution models, if you just take that background and if you calculate the eigenfrequencies corresponding to that, it already is extremely close to what you observe. But we know there are differences.
So you're using the observations to sort of post-fact to justify the linearization.
And that is how the standard models are even justified, because when you put in a magnetic cloud and you let it simulate over a billion years, the reason why you believe that is a sun, because it has the same luminosity, mass, and everything else that you observe. So yeah, that's, I mean, I've never done these simulations myself, but as far as I know, that's what happens.
Okay, yeah, because there are these big concerns about, in dynamo theory at least, about a similar perturbation analysis to sort of infer the mean field alpha effect where you throw out the higher order terms. And there is a big debate in the community whether this is possible or not. But I mean, I think, your justification is fair enough in terms of comparison to the observations.
So I would to keep it simple, I would only say this: people have believed differential rotation, but again over there, what you keep are terms up to first order.
Right.
And you could go on to higher order perturbations, but that would account for changes which possibly you cannot resolve.
Small percentages and you can't resolve, so don't worry about it.
Exactly. So now your equation is
Srijan, what is the small parameter in your perturbation theory?
It depends on the perturbation that you choose, but for example, in our case, it is the fluctuating magnetic field that you have if you introduce a tiny perturbation which forms the waves.
Sorry, can I step in, Srijan? Is it okay if I answer this question?
Sure.
Small perturbation is the amplitude of these waves. So typically the amplitudes of waves are far, far smaller than the local sound speed, for instance, by 7 or 8 orders of magnitude. So linear theory works extremely well. That is the only approximation. The equation would be like that.
Shravan, did you say amplitude of the small perturbation or much smaller
Small
than?
amplitude theory, it's a small amplitude theory. So the amplitudes of these waves or these fluctuations are very, very small. So second order terms are much smaller than first order terms.
So the amplitude themselves are the small parameter.
Yeah. So I mean they're very small. So we ignore second and higher order terms.
Okay.
All right. So let me kind of.
There was a question in the chat box. I don't know whether you saw it already. By Debesh Bhattacharya. It's difficult for you to see it while you're giving the talk.
I'm not seeing it.
Yes, I'll just read it out for you. So Devesh says that Srijan, it seems that the K as a function of R term has some relation with the temperature as it is higher close to the solar surface. Could you explain this issue?
Right. So this is something that I'll come to at the end. So when you think about temperature, you're talking about that all of this is related to the thermodynamics, which means the sound speeds. And if you consider a complete theory which accounts for perturbations in flows, pressure, density, sound speed, and magnetism, you'll see that magnetic fields and sound speeds inversions are slightly ambiguous. And I'll touch on that a little bit in my supplementary slides, but I would like to postpone that because I have some more things to cover right now. So I'll come to that when if I reach that point. But yes, you're right. The kernels should account for that as well. All right. So if I may go forward, I'll just draw your attention to a small detail here. Don't look at anything other than the highlighted box. You see there is a 1 plus p sitting in the kernels itself. And p is minus 1 power L prime plus L plus S. So L and L prime are the two modes. Think about the spherical harmonics we talked about. And S is the perturbation. So this is like the picture of the the integration with the three spherical harmonics that we have. So now if L and L prime are the same, which is called isolated multiplet approximation, which is used to do differential rotation, then you can only infer S when it is even, because otherwise 1 and minus 1 would cancel each other out, rendering zero sensitivity. And this is where mode coupling comes in, because in mode coupling you can start considering modes which have different angular degrees, which is L and L prime are different, which is when S can be odd. So we need to go beyond traditional techniques. All I've told you about till now involved these beasts called spherical harmonics, which means that we are looking at the whole sun. But then to look at smaller structures, which is what people do in local helioseismology, we need to look at a tiny patch. And in a tiny patch, all these ripples that you see on the surface, if you zoom in a lot, they become plane waves, which is shown on the right here. So we move from this YLM as the basis to exponential IQX, and this is at the heart of Cartesian mode coupling. And here I briefly show what you would see for supergranules. The interconnected yellow patches, yellow lines kind of demarcate different supergranules, and you can average them out, and you can have one supergranule which will share the common properties between all supergranules. And then you can find how it looks like in the spectral space, which is in the QX/QY space, which is wave numbers. And this is how these rings denote that the major amount of energy is contained somewhere in L equals 120. And the measurements that we use are called B coefficients. These are just details, but the way we get B coefficients are from these things called phis, which are mode amplitudes. So if you just take the surface and you decompose that into modes, they will have a certain amplitude with which they're like fluctuating. And you can do a cross correlation of these over certain times, and you end up with the B coefficients. So the B coefficients in the geographical map kind of look like this. And the main challenge at this point is to how do you take this map and you infer the structure underneath with enough signal to noise for you to confidently say that, okay, this is what the structure is. That has been the primary challenge in almost all of helioseismology, to have a higher signal to noise. So when we are writing perturbations, which is P of XYZ, which is distributed in a certain way, in the horizontal and in depth, we use the plane wave basis, right? Because again, we are looking at in a box with periodic boundaries, and it has a certain perturbation. So there are two ways to increase the signal to noise of our inversion. One is to increase the signal to noise of the measurements, but these are unfortunately related to what the satellite does. So that's kind of beyond our control. But then what we can do is we can carry out an efficient parameterization of the whole perturbation. So the lower the number of unknowns, as you can imagine, the better the data is going to constrain it. So if you have two unknowns and you have 10,000 data points, those two unknowns will be much better constrained as compared to if you have 2,000 unknowns and 10,000 data points. Until now, in in Cartesian mode coupling, people were using plane wave basis. So as you can see in this image on the right, the plane waves come from all directions, and all of these would make up this circular structure, which is, let's say, a sunspot. But then you would need some thousands of them to make up that entire structure. But then how do we reduce this, right? So the way to reduce this would be to choose a certain basis which has that inherent structure already in there. So if you have a basis which looks somehow circular, then you can imagine you would only need 3, 4, 5, 10 of them to reproduce what a sunspot looks like. And that is exactly where Slipian functions come in. All right, think about a function g of x in the horizontal, right? And then what we are looking for is a certain patch, which is the sunspot, which is a circle in your let's say in your observation, and you want to create your basis functions which are optimally concentrated within that circle, and then nothing beyond it. So we have this parameter lambda, which is nothing but the energy of that basis within the patch, which is script r, over the entire domain, which is r squared. So as you can see, if lambda is 1, then it is entirely contained within R, script R. If lambda is 0, then it is absolutely not inside the domain we are in of our interest. And this leads to a certain eigenvalue problem. I'm not going into the details, but we have to do it numerically. And we end up with basis which looks like this. And this is what I was trying to drive home when I said that we need to have a basis which looks nice and circular. I'll show you that if we use these things as basis functions, at least for a circular perturbation, it leads to very, very few coefficients compared to 3000. So if you follow the red dot here, that is the value of lambda, which means if it is close to 1, the uppermost dash here is 1. It means that this entire basis is completely space limited within the domain of interest, which is the red dash, which is the black dashed line. So as we start moving towards lower and lower lambdas, you see that there's a faint leakage of the basis outside. And this is in log scale. So even if it seems like it's a lot, but it's really not a lot. But this ends up giving us basis functions which are constrained, which are limited within the sunspot area and has the desired geometrical structure. So this is a very nice picture from one of the papers on Cartesian Slipian functions, and this is just to show that you can choose an arbitrary patch in your geographical region, and you can end up with these nice basis functions. You don't only need these to be circular, which immediately means that we can start looking at active regions. And this is the final set of slides that I have to show you how 3000 coefficients come down to as low as 3 or at max 20. So these are the B coefficients that I showed you before. So these are the observations, right? This is what we kind of observe. It's not the most straightforward thing to imagine how you would get this from the measurements, but for now, let's say you see this when you look at supergranule. On the left is what we have as the original map. And as we know, the supergranule has an extent of plus minus 30 megameters from the center of the supergranule. So that's where we have the circular black dashed line. Now, what we want is to reproduce the structure contained inside that spatial region. And if we use the Slipian functions, the basis that I showed you before, what you get on the right is the reconstructed image, which does not care about anything outside it, but cares about everything that's inside it. On the lower left is the plot of the coefficients as a label of the coefficients. And you see that there are at most 1, 2, 3 peaks. So that means there are 3 effective number of basis functions that you need to construct a circular patch, which is space limited. So we have brought down the problem from 3000 unknowns to 3 unknowns, which means that we have for every unknown, we have 1000 more constraints to really give us a high confidence inversion. And we can keep doing this for different branches or radial orders of measurements. And this is the P1. So they look slightly different. But then if you go to P5, what happens is you see a little more noise. The signal to noise reduces. But still, within the black dashed circle, you see that you reproduce the B coefficient measurements very, very, it's pretty good, I think. Okay, not exact, but I think this is good enough, given that it only takes 20 effective basis functions as compared to 3000. So these are measurements for flows. So if you use this, you can infer what sort of flows exists under a supergranule. But then if you look at measurements for magnetic fields or sound speed anomalies, this is how it looks like. Now this has a little more, the structure is a little non-trivial. It's not perfectly symmetric around the center. So again, we see that we get pretty good reconstructions using the Slipian basis, and we only did 9 effective basis functions. And yeah, we can keep doing this. And once again, for the one which has very low signal to noise, the reconstruction is pretty good. So this is what we will use as our inversion. This is how we'll parameterize our inversion with only 20 effective basis functions. And so this brings me to the end of the slides, at least without the supplementary part. And of course, I've not done this alone. So for the global magnetic fields, I worked with Puneet, who was in TIFR, working with Shravan at that point, but now is in ICTS, and my advisor, Jeroen Trump. For the Cartesian coupling cases, I'm in active collaboration with Christopher Hansen of NYU, Frederick Simmons of Princeton, and Prasad Subramaniam, who is a student at TIFR, as well as Samarth, who is one of the attendees of this meeting. This work on Cartesian mode coupling that I'm doing over the summer is funded by the Elizabeth H. and Darren F. A. Award 2022. Yeah, that's how I'm sustaining myself. And finally, I would leave you with the summary slide, which shows that what we have really done is found kernels for the global system. We have extended the same thing to the local kernels, where you can use this in a Cartesian patch. We have been looking at Slipian basis for effective parameterization. And what I have not touched upon is where I guess Devesh's question comes in, is when you account for the entire inversion, including magnetic fields and sound speed, there's a tiny ambiguity, which is shown by the fact that sound speed and the horizontal part of the magnetic pressure share the same kernel. So it might be hard to infer them unambiguously. So what you would be inferring is a combined measure, is a combined quantity.
Sorry, what was that again? Sound speed and magnetic pressure, is it? What was that again? Can you repeat?
It's the horizontal, so it's bx squared plus by squared. It does not have the bz squared.
All right. Okay.
So these two, have the same kernel form. Yeah, I guess that's basically it. If people are further interested, there is a very nice toy problem that we have in our 2020 paper, where we assume that the core has a toroidal field, the outer part has a dipolar field. So that's how it looks like, and there is a transition region in between. And all of this can be very neatly worked out in the generalized spherical harmonic basis. And if you use this as your, the magnetic field that exists in the system, you can start predicting what sort of observations you would see, which is summarized in this table. And since I've also mentioned this can be used for stars, I have, we have investigated a parameter space of different strengths of magnetic fields, which you can see in an active star. And you see that for those, the measurements become much stronger. It goes from practically from 4 to 400. So this could have implications in inferring at least axisymmetric magnetic fields for stars using astroseismology as well. So with that,
it's a great question for Shravan also. I don't know, has there been any attempts to utilize such stuff for planets, like giant gaseous planets, where you might have some seismic signatures of seismic stuff on the surface?
So when you say planets, when you said this stuff, you mean magnetic fields or
magnetic fields?
Well,
I mean, I know that this is being applied for a long time in for stars, but just curious about ground
the fact
law.
that the fact that there were no kernels for magnetic fields, I think means that it was never applied. So now
you might
we
want
have
to
kernels.
explore that, because this is an exploding field, right? I mean, anyway, we can talk about it later.
Yeah.
Can I ask a quick thing?
Sure.
So it seemed to me that in some parts you are basically thinking there is a vertical magnetic field. But in that case, when you are thinking of sunspots, your magnetic field is already there. You can at least see it on the surface.
Right.
The more interesting case is when the magnetic field actually active region of the sunspot has actually formed.
Sorry, your voice is breaking up.
I'm
Can
sorry.
you?
When the active region of the sunspot hasn't actually formed.
Hmm.
I think that's the more interesting case, right?
So the thing is, we have not really assumed that there is a vertical magnetic field. The magnetic field can have any structure, and
But the circular symmetry of the Slipian function
mhm.
will not work if you have a horizontal component in the magnetic field.
um,
That will spoil your rotational symmetry about an axis.
okay, right. So the reason why I am showing a circular patch over here is only because I was trying to show supergranules.
I
But
see.
if you have an
That's fine.
active, if you have an emerging active region, and this is purely me speculating at this point, we would not choose a circular basis. We would choose an arbitrary patch, which we somehow would expect, inspired from observation, and our basis functions would start looking like this arbitrary basis that I showed you here.
Interesting. Thank you.
Yeah, I
Very
guess.
interesting talk. Thank you.
Thank you so much.
Thank you so much, Srijan, for such a wonderful talk. If anybody has any further questions, you can unmute your mic, or else we'll move on to the next talk.
I just have a quick question. So, since you're talking of other stars also, um, so how so when looking at other stars, you don't really have spatially resolved observations, right? So how I mean, whereas for the sun you have spatially resolved observations. How does that impact the inference of, if let's say we're trying to find out the magnetic field?
Right.
How would that compromise you in any way, if at all?
It will compromise. I mean, it compromises us in the same way as it compromises us from inferring, rotation to a certain extent, not rotation, flows for other stars. So when you're looking at this, we have to think about, for the sun, let's say sun is a star, which means you
Right.
integrate out over the entire surface. So what you would end up with are modes which will not go too high in L, at least for other stars. And which is why when I mentioned about other stars, I put a small caveat that you have to kind of stick to the axisymmetric fields.
Mhm.
Uh, might
So
be
the
better.
large scale mean fields, sort of axisymmetric fields,
Right.
that's
Yeah.
what you can get a sense of.
Yeah. Yeah. I think so.
Okay, and by that, do you really so you mean is it, can you separately distinguish between the toroidal components and the poloidal components, or you're or not so?
You can, but then when you think about toroidal and poloidal as two different components, what will happen is these will at least be two different unknowns, and the more the number of unknowns, the more you need your, like, as you increase the number of unknown, that comes with the penalty that the signal to noise for each unknown reduces. And since
Okay.
other stars already have such weak measurements, we would ideally want to have the minimal number of unknowns. So in principle, yes. In practice, I'm not sure.
Okay. All right. Thank you for a great talk.
Thank you so much for listening.
Thank you so much, Srijan. Our next talk will be delivered by Dr. Shubhamay Chatterjee from the Southwest Research Institute. He would be talking on leveraging a deep learning model to efficiently label solar flux emergence videos. Shubhamay, uh, please take over.
Thank you, Sita, for the kind introduction. I'm sorry, my voice is really bad. So feel free to interrupt me, and if you don't hear anything, I can answer it for you. Let
Umar,
me
where
go
are
ahead
you? Are
and
you in Boulder or are you in
I am
Hawaii?
in Hawaii. I'm in
Man, all of
Hawaii.
you are in
I
Hawaii. I
have
mean,
been
everybody I talk
feeling
to is in
really
Hawaii.
sick.
COVID,
Yeah, yeah,
BA.2. Okay, all right.
yeah,
Well, take care.
yeah. Thank you. I'll
Drink
go
a lot of
ahead and
fluids and
share my.
rest well.
Yeah, I'll try my best to go through it fully, but
Yeah, if you at any point if you feel tired, you're
yeah,
fogging out, I mean, just let us know because I gave a talk. I mean, I get two talks last week. One of them was I had COVID and I was fogging out. I mean, it was tough. So yeah, let
yeah, I
us know
totally
if you
understand. Yeah,
if you're kind of
sure, sure.
yeah.
Yeah. Do you see my screen? Fine.
Yes, we can see your screen. Yeah.
and you can hear me fine, right?
Yes.
Okay, so this is Shubham. I am a postdoctoral researcher at Southwest Research Institute, Boulder, Colorado. And this is a recent work that we have performed to use a deep learning model to efficiently level a set of solar magnetic flux evolution videos. So this is the brief graphical abstract for this work. So we used solar active region evolution videos from Soho MDI, and we ask 3 questions here. So whether we can start with a crudely leveled videos with a set of crudely leveled videos, and we can refine the leveling as well as we have as we are limited by the data set, whether we can train an ensemble of models instead of a single model to estimate the classification uncertainty, and lastly whether we can repurpose the deep learning model to do a higher level task that it was not initially trained for. So before I go into the actual work, I wanted to tell you how the machine learning, which is traditional machine learning approach, largely differ from the deep learning approach. So here you can see there is a classification model using classical fully connected neural network. And the problem you want to address is, given a vehicle, you want to classify it into car or not a car. But for the classical models, you need a feature extraction step. So and that brings subjectivity into the picture, because you never know how many features are good enough. So in deep learning, you avoid that feature extraction step. Instead, you can feed that model directly with an image, and that model will discover the most relevant features to arrive at the expected outcome. So let's see how that is done for the deep learning models. Um, so you can see here, this is the image on the left. You see an image of a dog, and let's say this image has 1000 by 1000 pixels. So you have, if you now treat each pixel as a feature, you have 10 power 6 features. And now let's say we have an internal hidden layer with 1 million hidden units. And if you multiply now both, you will have 10 power 12 connections, and you can totally understand how much computational burden it will place on the resources. So instead, what scientists found, that if you, instead of connecting all the pixels in the image to a neural network node, if you can do it by parameter sharing and with a limited field of view, which is convolution, right? So the idea behind that is because these images are locally structured data, so you don't need to see the entire image to find relevant features. So this is just one layer of convolution, and you can cascade these convolution layers with subsequent nonlinearities. Now, if you don't employ nonlinearities after each layer, it will not make sense, because convolution is linear, and cascade of linear operations will give you another linear transformation. So that is where the nonlinearity comes into the picture. So when you do that layered architecture, this is what you find. So you see, let's say you feed it with a cat's face, and the initial layers of the model will learn such features which are much lower level, and as you go deeper, it will do a higher level abstraction, and it will understand much bigger features. So that is how a deep learning is really utilizing the inherent features in such higher dimensional data, and to discover relevant features without any explicit feature engineering. um, so this kind of gives the hint. So do you see the videos fine? I mean, I don't know, the internet here can be a
Yes.
little asynchronous for you.
No,
Okay,
the videos are
so
working.
okay, thank you. So these are video data, and you can see the dynamics on here, and you would like to ask questions such as where evolution is happening, what it corresponds to, and when it is happening, right? These are the key questions that you can ask. And deep learning model, as I said, are really efficient in processing such higher dimensional data. Um, so the problem we really focus on is to distinguish between solar active region evolution videos, where you see new emergence happening, like the one on the left. So if you look at the patch which is in the Carrington grid, in 15 degree by 15 degree latitude longitude, and the pixel resolution is so 6 pixel corresponds to 1 degree in both latitude and longitude. So the reason we do Carrington rotation is to nullify the shift of the regions and roughly have them aligned across the video. And on the right, what you see is an evolution of active region where you don't see any new structure emerging, and at least in this resolution, right? So we collect a set of 2400 videos with each frame of 90 pixels by 90 pixels, and 225 such frames with a cadence of 96 frames, which is typical for Soho MDI. So before training a model to classify these videos into non-emergence or emergence, we need to put some ground truths, right? And that ground truth is created by the bipolar active region catalog developed by Andres. And for that, he employs active region detection once every day, and he also applies a heliographic longitude cutoff of -60. So anything before that is placed level as non-emergence, because it is considered as a returning active region, and anything on the right, depending on when the emergence is detected, it is considered as an emergence or non-emergence. So as you can clearly understand, this is quite a crude level, and this cannot be entirely correct. But it takes a lot of time to manually verify each and every video and put a level for the videos. Instead, we develop an iterative approach in this study. So we initially train a model with the crude dataset, right? So instead of a single model, we train an ensemble of models, and this is the architecture of the model. We have this again 90 pixel by 90 pixel by 225 frames of videos, and then there are these convolution blocks followed by non-linearities, and there is this max pooling, which is changing the resolution of the patches. So at the later point after max pooling, the convolution kernels are seeing a bigger field of view. That's how it is learning lower level structure to higher level structures through the network. Ultimately, when you repeat this thing, convolution, nonlinearity, max pooling, so you get a vectorized form almost. Then you flatten this, and then you apply the conventional fully connected neural networks to arrive at the outcome, which says whether it is an emergence or not. And this is the training, validation, split, and test set. So we keep aside the test set for every year for 2 months, November and December, and we break the rest of the months into non-overlapping training and validation blocks. And the non-overlapping approach is because through the validation blocks, we want to look at the entire set of videos that is the model is trained on. So once you train model 1, you look at the validation set for the model 1 and see for how many videos the crude levels disagree with the model inference, right? And after that manual verification is done, you correct the mislevels. So it can be that the levels were incorrect and the model was correct. In that case, you uh, uh, correct that mislevel. If the model was incorrect and the original level is correct, you don't touch it, right? And you do it for each of this training validation combination to look at entire set of videos. And then we iterate this entire process until we find convergence. If you look at now the performance after these iterations, you see this is a bar plot, and this yellow and blue regions are where, so yellow is the one where your CNN or the convolutional neural network was correct. So level changed, but the blue one is where the level was unchanged because the convolutional neural network was wrong. So so in the next phase, you don't look at, after training, you don't look at the videos which were previously looked at, right? So you find the new disagreements and again repeat that process of uh, correcting the mislevels. And when you keep doing that, what you find at the end is your model is actually learning to generalize, right? So if you look at the ratio of yellow to blue, you can see at the higher pass or higher iteration, the model is much more correct as compared to the original mislevels. That means even though there are problems in the data, model is understanding to identify or distinguish between the right and wrong. And also you see this convergence through this plot here. So this dark uh, circles here at the initial pass one, right? And these numbers here at the different training validation blocks, right? So on the x-axis, what you see, what is the accuracy of the model, and as you can see, as you go to the higher passes, the accuracy improves as well as the requirement of changing mislevels reduces. And if you can look at this in another way, if you now just take the ratio, as I was saying, that as you are going to higher passes, it turns out that the model understands which are wrong and which are correct. The gray ones are the ones at the highest iteration, and you can see how the accuracy across the training validation blocks are converging, and also you are getting a much better ratio, which should be closer to 1, which b is here how many times the model is correct, and c is how many times the original level is correct. So you can clearly see the convergence there. And so in a nutshell, this iterative process that we developed, we started with 2032 videos. And once we fully manually verified that to do the validation of this approach, we found there were 60 mistakes in this, which is 32% of the total. And then after we went through these 4 iterations, we ended up correcting 550 of those 650 mislevels, and this was only after verifying half of the entire set of videos. So you can clearly see we only check manually 50% of the video, but we end up correcting 85% of the mislevel. So that is the value of this iterative approach. So you don't need to have perfectly leveled data. You can utilize the deep learning approach itself to in an iterative manner to refine the data leveling. So now that I have defined the leveling refinement process, the next phase is whether we can um, find the classification uncertainty using the ensemble of models. So to motivate you why classification uncertainty is important, this is an example right here. So you have an image classifier which is trained to see 2 different faces, which is there in the x-axis here, right? And if you feed the model in the test phase with one of those faces, it will give a confident result because your test set data is well represented in the training set. But when you give an unknown data or unseen data, which is neither of those 2 faces, you would expect that the model will be quite neutral, right? It will give a probability for both the classes as 0.5 because it is neither of them. But what you see in real is these deep learning models are actually confident, and it predicts that image to be of one of those classes, right? And which is entirely incorrect. So what if instead of training a single model to do this, we train an ensemble of models, right? So in that adds additional value, right? So if your test data is now well represented in the training set, the models will tend to, the ensemble members will tend to agree with each other. Whereas you see, if you show the model an unknown data, which is not well represented in the training phase, they'll tend to disagree with each other, right? So instead of having a single outcome which is totally off and being wrong, it is better to have an uncertain outcome so that it is actionable. um, so that is the approach we take here. Instead of training a single model, we train an ensemble of model. Then we tune the cutoff using a threshold by optimizing precision and recall, and we find this outcome, right? So you can see here true and false predictions for the set of videos in the test set, and we divide that into the stable and unstable inferences. right? And you can see in the unstable inferences region, even though the median is higher than the tuned probability threshold. So y-axis is the emergence probability of emergence happening within the video, and x-axis is the video index, right? So and this gray pixels are the histogram density. So you can see even though for the unstable inferences the median is greater than the threshold, there is this spread which contains that threshold. So now instead of a single model, if you had one of the models, if instead of an ensemble of models you had one of the models, then and if it predicted this right here, so it will be quite off, right, from the reality. So instead you are finding a spread, and looking at the spread you can take efficient decision whether to believe on the outcome of the model ensemble or not. So darker the pixel is, higher number of models are saying that the probability is within that bin. This is what we find. And also if we break our test set into solar cycle phase, we don't find any systematic effect on the classification accuracy of the model. Now comes the next question. Now that we have trained a model to look at the videos and say whether it is an emergence or non-emergence, whether we can find where in the videos, where in the frame sequence the emergence starts. So instead of retraining the model, we develop an approach to mask the videos, right? So what we are doing right here, we are masking all the frames from the end till this frame 130, and then we are replacing all the masked frames with this frame number 130, and then passing it through the trained model ensemble, and we do this till there is a change in the inference, right? So in this case you can see 85, the emergence is just starting and it is truncated till here, and then we replace everything after that with the 85th frame. So when you do that, you find this. So you have, this is a typical emergence video, and you see the color code is representing here how many model at that phase of the video is thinking. This corresponds to an emergence video. So you can see right here, if you look at the color scale at this phase, only 2 models were thinking this video corresponds to an emergence. But when it grows bigger, you see the number of ensemble members that tend to think this is an emergence video increases, and it saturates ultimately. So this is the approach that we take to use the model ensemble and repurpose them to find the time of emergence. And these again, we have this ensemble of models, and at each truncation level we take the inference of the model and see the spread of that, and see where the median prediction goes below that tuned probability threshold of 0.6. Or you can, or there is another approach where we take the median and take the gradient of that at each frame number and see where the gradient is maximum, and that is what we call as the time of emergence, right? And if you now plot the ground truth times at at which the emergence is starting and the prediction, you find a more or less match, which is concentrated little above the y equal to x line. And keep in mind that this model was never tuned to predict the time of emergence, it was just repurposed. So once you tune this criteria, you can totally align the detected time of emergence with the ground truth time. So this kind of opens up the model. Instead of using the black box deep learning model, you are actually trying to understand by tweaking the data where the emergence is happening. And as you can see, it is able to understand where the emergence is happening. This kind of says that the model is giving the right answers for the right reason, right? And then if you again plot a 2D histogram like before with the video number and the predicted time minus ground truth time, you can see a small shift, right? It should be centered at 0 if the predicted time was exactly, median was exactly matching the ground truth, but there is a small shift. So again, that is because of the fact that this was not tuned. This was just the repurposing of the model. Now the next question, so if emergence is happening and if we know when it is happening, can we say where it is happening? And that is where we bring this approach called saliency analysis. This is an interpretability approach of typical deep learning models. And so for that, what we do is we find the pixels where a small change in the value will cause a large change in the predicted probability, right? So it is basically the saliency map is the gradient of class probability with respect to the pixel value, and wherever it is maximum or wherever it is brighter, that means that is the region, the model region in the emergence video that the model ensemble is paying attention to. And you can see that is more or less aligned with the median frame of emergence with this bipolar region. And that again says that the model is all not only finding the right frame of emergence, it is also looking at the right place of emergence, right? uh, so to summarize what we have found right here is deep learning, you don't have to get a fully like very well uh, leveled data. You can start with a crudely leveled data. It doesn't need to be perfect, and you can actually train a deep learning model to accelerate the leveling process and correct the leveling in much faster way than doing it entirely manually. um, we also showed that the deep learning model can be repurposed to do a higher level task than it was originally trained for, and both the emergence epoch identification and the emergence site identification increases the transparency of this model. Um, and also having the model ensemble adds value because this data set is not really large, only 2000 videos, and if you are training a single model, it will be highly unlikely that the test data will be very well represented in the training data, and then the model outcome can be totally off. So instead, if you can train an ensemble of model, you can estimate the uncertainty in the detection, and accordingly you can take appropriate decisions. So this work recently got published in Nature Astronomy. Please, if you are interested, please have a look at it. And we also published the MDI active region evolution videos, which are labeled to emergence or non-emergence through Harvard Dataverse, and it can be publicly accessed. Um, so the next phase is inclusion of different surveys to make a more diverse. So by this I mean that now we have done only with MDI, it can be extended to HMI, and also by that you can have a bigger data set, and you can just constrain your uncertainty in a better way, because in that with that you will cover a bigger span of the solar cycles, and it will be less unlikely that the test set is not well represented in the training. um, and also we aim to do this highly ambitious task, which is prediction of flux emergence, looking at the early evolution of um, active regions. And so so there are different approaches to deal with the causality that is embedded in such videos, and whether you can predict when the emergence is happening, and how early can you predict that, whether you can set a limit on that. So that is our also one of the aims. And also we would like to see how general this approach is, and apply this to other astronomical data set, and see if we can iteratively improve the leveling of data sets in astronomy which are crudely leveled. And also this is another work we are currently pursuing to see what are the finer demarcations within emergences and non-emergences, whether there is a large class imbalance or not, and if so, whether we can improve the class balance by including more data set, and if it is if this imbalance is inherent, then can we train an ensemble of models and make the predictions more actionable. um, yeah, so that's what I wanted to say today. If you have questions, I'll be happy to take them. and these are the QR codes, and you can scan, and that will take you to both the data and the paper.
Thank you so much, Obama, for such a nice talk. If
No problem.
anybody has a question, you can unmute yourselves and ask. Yeah.
Shubham, I don't want to bother you too much
No problem.
because you already gave a talk and your voice is not in good shape.
No problem.
But I was just wondering the applicability of what you have done. So this is, I mean, technically quite a nice bit of work.
Great. Thank
Now,
you.
essentially, what you are trying to do here is to find, is to generate an automatic sort of machine to identify flux emergence, right?
Right.
Identify new
Yes.
emergences, new active regions.
Right. Yes.
But then you said that you don't have a timestamp on this. Uh, that is
Yes.
going to seriously compromise this, right? So why is it so difficult to build in a timestamp? I mean, if you are
Yeah, we bring in a timestamp for this, the repurposing task, because we had to quantify how closely the repurposing matched the ground truth timestamp. So for that, we did that. We
and
selected a
using
set of emergences and
okay, and using your data, is it possible? Let's say I want to ask you, what is the
yeah,
typical profile of DeFi DT when a new active region
okay,
emerges, averaged over all the active
right,
region emergence in the history of observations that you have? Can you give it to me easily?
right. So that for that the approach will be either an algorithmic approach or opening up the model and see how it is detecting the emergent sites and see how that phi is changing with time, and then do that derivative and
Right. So we
uh,
look at some further
effectively combine
processing.
those.
Okay.
Yeah. Yes. Yes.
Because that information would be quite nice, actually. I mean, once you can start getting some
Okay.
physics out of this database, extracting
Right.
physical sort
Right.
of insights on physics
Right.
of flux emergence, that will start make it
Right.
much more interesting
So
for
so
us.
currently we are really thinking we will try and look at the precursors using the deep learning model to identify flux emergence before it actually happens. And then if we can make the model interpretable, I
Okay.
know it is very ambitious, but
No,
yeah,
all of us are various
we
people are
can.
interested in the same problem, it looks like. So maybe I think we should form
Yeah.
a team to look at this together at some point in time. Because, well,
Yes. Sure. For sure.
all right. Okay. Yeah, I think there's some questions in the chat box. Yoshita, you can go ahead and ask the questions in the chat box. The people can directly ask whatever.
Right, yeah. So there is a question from Ashwin Amartharaj. Uh, the question is, does the variable rotation make it difficult for time determination? I think, yeah.
Uh, as I said, there is no, like, you cannot find it is biased to uh, one of the types of videos. You find this bias across the videos, emergence videos, right? So it is not specific to one type. So that most probably comes from the approach that we employ to repurpose the model, the threshold, right? Let me show you. Yeah, so right here, so we are saying that, okay, where my gradient is maximum, that is my um, time of emergence. Instead, if I developed an approach which is before the maxima, then you would nullify this um, delay that we are seeing in the emergency epoch identification. I mean, this delay is just about half a day, but if you change the criteria by which you detect this epoch of emergence, I think you can nullify the bias.
Uh, this is Subhadeep. I have one doubt in.
Hi,
Can I
Shubhadeep.
ask? Yeah.
Yeah, sure,
So
sure.
um, in the last plot, what you were showing that the gradient higher the gradient peak and the from the probability threshold. So in
Yeah,
this is for testing out the model's output, right? When the emergence time start of the emergence time from the model
right.
output from the ensemble.
Yes,
But I was just
yes.
curious. I mean, how in the for the generating the ground truth, how we are basically
So we
determining
are
the
we are
emergence time,
collecting
because
these
it's a continuous
emergences.
process. I mean, Yes, can you
Right.
please?
So we are collecting the emergence videos and manually looking at the videos to find where the emergence happens. So that is something which is necessary to say that your model is actually working, right?
No, no.
So
So
that is manually done.
yeah,
The
so
ground truth time.
where the
Exactly.
emergence is happening, that we can see from the image, but defining the
Yes.
particular
The
emergence time, that is it's not
right.
clear.
That is manually done. The ground truth is manually leveled
So you are
to
basically checking
validate the
some.
model outcome.
Okay. So the is there
Yeah,
any
set of
threshold?
emergence videos.
Okay.
Yeah.
Now I want to say, I mean,
Yeah.
is there
Threshold is
any
that.
threshold? I mean, you are checking the amount of flux which is over time period, and if there is a certain
No, there
threshold.
is we don't do it based on flux. We do it based on the probability. So the probability of the median should be greater than 0.6, and along with that, we should get a maxima of the gradient of the probability with a frame number. So if it satisfies both the conditions, then you consider that as the time of emergence.
Okay. Yeah. Thank you.
And also you find the uncertainty in the detection because we have an ensemble of models, as I said.
If there are further questions, you can unmute your mics and ask.
Well, so since it doesn't look like there's any other questions, Shubham, I just wanted to thank you for taking your time out. Must be pretty late in the evening in Hawaii.
No
And also,
problem. It
you're
was my
recovering. I mean,
pleasure. Yeah.
same thing happened to me last week, a couple of weeks back in Bern. Anyway, so recover quickly. All the
Okay.
best. I think it's a
Thank you.
mild strain, so I think it should be okay in four
Yeah,
five.
hope so. Yeah.
Yeah, just rest and drink
I
a lot
will
of
just go
fluids.
to the emergency and get checked. Yeah.
Yeah, and drink a lot of fluids and don't get psyched out. Drink a lot
Yeah.
of fluids and rest, and you should be fine.
Yeah.
Get some vitamins and buy paracetamol. Paracetamol is you can get it off the shelf if you have fever. Uh,
Yeah.
of course,
Yeah.
nothing like seeing a doctor if you can get it done in the so,
Yeah.
yeah. All right, I think we'll be fine. Don't worry. All the best.
Thank
Take
you.
care. All right. Bye.
You too.
Thank you so much,
Bye.
Shubham, and please take care. Yeah.
Thank you.
So I think we are at the end of our morning session. We'll break for lunch now, and we'll see you in the afternoon session. Okay. Bye, everybody.
Thank you, Shita. Bye.
Yeah.
Bye.